All right, so we're finished with integration. I know there was only one example. Taking a look at your homework, I didn't see a ton of integration problems. I kind of glanced through it. There were more differentiation and arc length problems. So what we're going to talk about now is arc length. So everything we've learned up until now, we're recasting in terms of parametric equations. And again, sometimes it's easier to describe a curve parametrically than it is to write down its equation. So let's remember, so if y is equal to capital F of x, so if I have, a function that describes a curve, then the arc length of that curve is the integral from a to b, square root of 1 plus dy dx squared dx. And this is from section 8.2 from the beginning of the week. Assuming that you are watching these chronologically, I record all of these in about a day, so for me it was this morning. Actually, I think I did that one earlier. It doesn't matter. Anyway, so this is the form of the integral here. But you'll remember that, for parametric equations, if we could describe this thing instead as a parametric equation, x is equal to little f of t, y is equal to little g of t, then what we're going to have is dy dx is, it's going to be so let's go ahead and just do this in terms of y and x. So this is going to be dy dt divided by dx dt. So what this is this is going to be the integral from a to b, square root of 1 plus dy dt divided by dx dt squared. And then I need to calculate dx. Well, so dx is going to be, so if I just do the differential, dx is going to be dx dt dt. So instead of writing f prime, I'm just writing dx dt. So now, instead of dx here, I'm going to have dx dt dt, and you can think about these as, so a good mnemonic is, as fractions, the dt's would cancel and you'd be left with a dx. So what I'm going to do now is I'm going to write this as the integral from a to b, square root of 1 plus. So now I have this thing squared. So all this is dy dt squared divided by dx dt squared. And what I'm going to do now is I'm going to take this dx dt that's on the outside, I'm going to bring it inside the square root. But in order to do that, in order to bring this thing inside the square root, I have to square it. And it's going to multiply all of this stuff. So I'm going to get a dx dt squared here, dt. If I distribute that in there, I get the integral from a to b, dx dt squared plus dy dt squared over dx dt squared times dx dt squared. There's a square root around all of this that I've managed to turn into parentheses. And then I have a dt here. The point of this, writing this like this, is now these cancel here. What I'm left with is, if I can write this thing parametrically, the arc length then, and I should have changed bounds. So when I turn this into dt, these should have turned to alphas and betas because the bounds aren't the same. Let me fix that real quick. So this becomes the integral from alpha to beta, square root of dx dt squared plus dy dt squared dt. Let me kind of take a second to talk about why, so that changed to alpha and beta. So you can think about, these parametric equations when I have, them in terms, and I also have a function that describes this thing. I can think about these as being like a u substitution. So when I make a u substitution, I have to change the bounds of my integral. That alpha and beta is just supposed to describe the bounds for this thing. So the idea is, t t sits between alpha and beta. Alpha is less than or equal to t, less than or equal to beta. And so this gives me, you know, the length of a curve. So let's delve into this. So this is gonna again we're gonna get to a point where it's probably a little more theoretical than you'd like, but it's still good to talk about. This is for if I can write this thing as, you know, y is a function of x, and I have a parametric description of this. Now, what if I can't write y as a function of x? And so you'll remember the first time I went through and did arc length, I did this big long derivation where I split up the curve into these small lines that I then added up and it turned into an integral. You can do something similar. Yeah. So I'm not going to do the derivation here, I've decided. But you can do something similar if you're interested in it. It's the same idea. You use the mean value theorem instead of just for delta x or for delta y, you do it for both. And what you're going to find is the same formula holds. So you can go through the derivation in the book if you like. I'm not going to do it here because I did it for just the regular arc length case. So what if I can't write y as a function of x? The formula still holds. So you can use, so it's a mean value theorem kind of proof. So then we have this theorem. So if a curve, so this is important, I'll box it in, you know, underline it in red or something. If a curve C is described by parametric equations x is equal to f of t and y is equal to g of t, and alpha is less than or equal to t, less than or equal to beta, f prime and g prime are continuous on the interval, the closed interval alpha to beta. So this is a lot of math speak where I'm sure your guys' eyes are glazing over. And C is transversed exactly once as t increases from alpha to beta, then the length of C is given by that integral that I wrote up there. So it's going to be the length, it's the integral from alpha to beta, square root dx dt squared plus dy dt squared integrated over t. So that is my formula for this section, arc length. Okay, so let's talk about, you know, why some of this stuff in the theorem that is important. So obviously you want continuity and continuity of the derivatives. That's nice. But the thing that, you know, I hadn't mentioned before is it says transversed exactly once. So I'm going to do an example in the next video where we see what happens if that's not the case. But you can imagine, you know, if you had a curve that described, you know, transversing the same or going along the same curve twice, and you found the integral, or you found the arc length, you would find, you know, twice the actual length of the curve, like when you drew it. That's because, you know, what gets drawn really is going from one spot to another and then back to the same spot. So you'll get twice the length of the drawn curve. So I'm going to stop here this video because there are just 2 examples left for this section. We aren't going to do surface area because it's from a section that we skipped earlier. And there aren't any homework problems on it. So let's stop here and I'll jump into the last two examples.